fellowships along her academic career. She joins us today as a senior member of the IEEE, and has been involved in the IEEE Photonics and the Electron Device Societies, and has had governance experience in chairing the Photonics Society, the Electron Device Society, and the Nanotechnological Council chapters, which regroups a number of technical societies across the IEEE. She's currently chair of the IEEE Nanotechnology Council chapters and regional activities, associate editor of the IEEE Photonics Journal, and member of the boards of Optoelectronic Advances. She is a member of the Australian Academy of Science National Council on Materials Science and Engineering, secretary of the Executive Committee of Australian Materials Research, and Australian Research Council Advisory of Experts. So let me catch my breath. But to move on to some of her technical work, her research interests are in design, fabrication, and integration of optoelectronic devices based on 3-5 compound semiconductors. And today we look forward to hearing from her on some of that work on quantum wells, self-assembled quantum dots, and nanowire growth by metal organic chemical vapor deposition. So I see the slides are online. So Professor Fu, if you can take the floor, and we look forward to your presentation today.
Thank you very much, Matt, for your kind introduction, and also a very nice invitation from IEEE Photonics Society Montreal session. It's a great pleasure for me today to present our work on quantum wells in nanowires for optoelectronic applications. As Matt introduced, that I'm from the Australian National University. So just a little bit sort of introduction where we are to show where we are. So the Australian National University is actually located in Canberra, which is a city between Sydney and Melbourne in the sort of east coast line of Australia. Of course, however, Canberra is not a coast city, it's just a bit of inland, but very close to, 3 hours drive to Sydney, which is pretty easy to get to the coast. And Canberra is Australia's capital city. It is a very nice sort of only a small city compared to other big cities, about 400,000 population. And it has, it's called Canberra, Australia's bush capital, because it is, you can really see, you don't have to drive far from the city to see kangaroos. So when we have visitors, the things we do normally is at, evening time to drive them through some suburbs, you can see nice kangaroo around. That's always a very pleasant thing. And the Australian National University is, of course, Australia's top-ranked university. It's not very old. It's started in 1946, funded by the federal government. It is a very research-intensive university. We don't have very large undergraduate student number. We have in total student numbers about 25,000, maybe now it's about 30,000, but half of them are actually postgraduate students. And ANU is a very international student. We have a lot of overseas students from about 100 countries. And our group is called Optoelectronics and Nanotechnology Group at the Research School of Physics. So in our group, mainly we develop the material architectural growth based on mainly 3-5 compound semiconductors. And then we focus on researching low dimensional materials such as quantum wells, quantum dots, nanowires, and 2D materials. We also use that to explore their application in optoelectronic devices, such as lasers, LEDs, photodetectors, solar cells, and more recently we also start to also look at their application in energy, in sensor, a variety of different applications basically. So before I talk about my work, I would like to acknowledge really the past and present students, my colleagues, my collaborators, both within Australia and also across the world who have contributed to the work. I also like to acknowledge the Australian National Fabrication Facility, who has provided a lot of technical support and also equipment access to this work. As also this work's being funded by Australian Research Council, the Australian National University Ohio program, as well as US Air Force research labs. So just a little bit introduction for 3.5 semiconductors. 3.5 semiconductors, you can probably everyone knows that is basically formed by the group 3 and group 5 elements on the periodic table. By changing basically the different alloys, you basically can create 3.5 material with very broad band. Okay, so that can really cover by using different, by making different 3.5 alloys, we can actually cover a broad range of band gap from UV to mid-infrared, as you can see from this. And also we know that compared to the very well-known materials such as the semiconductor material as silicon, one of very important property of 3.5 semiconductors that they are most of them are direct band gap, which make them excellent with making them with excellent optical properties, in particular for optoelectronic applications. And also a lot of 3.5 material have very good carrier mobility, so which is also make them very important for optoelectronic applications. So you're probably all very familiar with a lot of optoelectronic devices used in our everyday life. So we know that lasers, LEDs that we use in our daylight, everyday lives, a lot of them are made from 3.5 materials. Photodetectors that we used for our spectroscopy measurements in the labs are made of a very good high efficiency detectors from indium gallium arsenide. They also can be used for infrared photon detection as well as imaging, such as the quantum well infrared photodetector. And of course, the most efficient solar cells is actually made by 3.5 semiconductors. So more recently, well, people are really trying to develop a lot of highly integrated function optoelectronic system that can be used in many emerging technologies. For instance, optical interconnects, the LiDAR technology that can be used in remote sensing, autonomous vehicle, smartphone, or more recently, a great interest in developing this AR/IR hologram system to actually to create a new metaverse is also certainly a system that needs use of the light as the main sort of information carrier for the optoelectronic integrated system. So to generate, manipulate, and detection of the lights is highly important and sort of for optoelectronic applications. However, so if you look at the global optoelectronic component market, there's certainly a very big market, and it's actually have a very about over 10% in so projected increase in every year. So you can see that this is I'm pretty sure there will be new sort of data coming out of the project, more sort of a large increase in the coming decades. And then if you look at, electronics integration, we're very familiar with the Moore's law, and which really nowadays people can really achieve highly integrated electronics with like billions of transistors integrating on small chip, right? But if you look at optoelectronics, the photonic integration, it is certainly developing much later in 1990s. And then even up to now, we can only integrate only a few thousands of components on the same chip. So most of, despite there's a huge sort of really growing demand for the photonic optoelectronic integrated circuits. So one of the typical platform used for photonic integration is indium phosphide photonic integration, where through the epitaxial growth and etching and a very complicated ray growth process, people trying to basically integrate the functionality of the light generation, transmission, and the detection on the same sort of substrate. So which consisting of the laser, amplifier, detector, modulator, and all these components. But one of the major challenge to that is that the regrowth, etching, and also integrate different types of semiconductor material with different band gap on the same substrates is very challenging. So there's like people are really looking at a lot of alternative platform. So here I'm going to really introduce you the platform that we see some potential, and also we've been working with based on 3.5 compound semiconductor nanowires. And I'm going to really hope to show you that it is a quite versatile, flexible, and miniaturized material derived platform, which can be really integrate many little nano building blocks used for the photonic integrated circuits. So in this talk, first I will give, of course, a brief introduction of what is the 3.5 nanowires, how we actually make them, and how we make them into devices. And then I will have a very brief review on some of the single nanowire device we make. And of course, then I will mainly talk about basically using this development of this indium gallium arsenide, indium phosphide quantum well nanowire arrays to show you like how we really develop our device from design and fabrication to the device demonstration. And if I do have time, I will talk a little bit about our work on also using top-down etching technique to making nanowire array detectors and the sensors, which we think is also another important alternative sort of approach, making nanowire array, which is a bit more cheaper and also probably also quite scalable technique. So nanowires basically, one-dimensional nanostructure that have this one-dimensional geometry. Normally have a typical the size of with the diameter about tens of nanometers to hundreds of nanometers, and we normally grow them into a few micron in length. And the nanowires, because of this very unique one-dimensional geometry, it has a lot of interesting optical and electrical properties, and as well as mechanical properties, right? So because of this one-dimensional geometry, when you grow using epitextural growth of these nanostructures, it actually be able to relax some of the fundamental limitation of lattice mismatch, thereby give us more flexibility in grow different material on different substrate or create some heterostructures. And also, because of this one-dimensional structure, the nanowires is able to support both localized resonance and as well as the guided modes. Thereby, we can really use the design of nanowires to modify the local density of the optical states, and use that for laser light emitting or the light absorption applications. And also nanowire certainly has very large surface area. So surface to volume ratio is very large. So you can really use it for applications such as sensors or photoelectrochemical energy applications. And moreover, we can also we have a lot of flexibility in do the device engineering. For example, if we have a PN junction, we can really create PN junction both in the actual basic along the nanowire length, as well as in the radial direction. So in this way, we actually can create this kind of geometry actually can really used for design of solar cells or photodetectors, where you can really use the whole length of the nanowire as the absorption volume, as absorption region. And however, you create the radial PN junction, can create sort of radial carrier collection paths, which actually be able to facilitate a carrier collection. So which have a lot of offer us sort of really additional degree of freedom to create to engineer our device. So how do we grow nanowire, or how we fabricate nanowire? So basically there's two approaches. One is the bottom-up approach using epitextural growth. And in this approach, a very common method people use is a so-called vapor liquid solid method, where we use metal nanoparticles such as gold. as a little sort of catalyst seeding layer to promote nanowire growth. Of course, you can use some colloidal metal nanoparticles and directly spray onto the substrate, or you can also use more sort of nanolithography technique to create a little gold nanodisc to really do a controlled sort of position control nanowire growth. But in this technique, basically, you can see you introduce a metal into the metal into your growth that might sometimes create some challenges in the device performance. And also the growth mechanism is based on this WLS technique. And then there's another way to create nanowires, the way most of our group is focusing on the selective area epitaxy, which we're using a dielectric layer as a template, and then we create nano holes on top of that and to design our nanowire array and grow them. So I will talk about that a little bit more in detail in the next slide. And another technique, of course, you can also create some etching masks on top of your substrate and using top-down etching. So this technique certainly have some its own advantage in some different application, which I will also hopefully be able to show you later in the last part of this talk. So let me talk a little bit about nanowire array growth by selective area epitaxy. So in this particular work, I mainly will talk about our work on indium phosphide nanowire growth. Certainly in our group, we grow a variety of nanowire structure as well as nano membrane and other nano shapes, which I will not have time to cover in this talk. So I will just mainly talk about how we grow indium phosphide nanowires here. So we normally start with the indium phosphide substrate, and we deposit a thin layer of silicon dioxide on top of that. And then we use electron beam lithography to design of the nanowire array patterns based on our some simulation work for different device applications. And so we combine that lithography with white or dry chemical etching, so we can open little nanometers of holes on top of the silicon dioxide, and then we put it into the MOCVD reactor to do the nanowire growth. So obviously we have to do a lot of optimization of the MOCVD growth in terms of the the gas flow rate, the group 5/3 ratios, as well as the growth temperatures to really achieve a good nanowire growth. So, so this is a SEM image of the typical indium phosphide nanowire array grow in our group. And based on this kind of nanowire structures, we actually can fabricate two types of nanowire device. One is a single nanowire device where we normally knock these little nanowires down and to transfer that into another substrate, in this case, the silicon dioxide on silicon substrate. And then what we do is that we're using electron beam lithography to fabricate contact on top of nanowires. So this is LEDs, single nanowire LED fabricated in our group. So where we have to do some standard device fabrication to make single nanowire device. So single nanowire device is a very nice sort of way to actually do some fundamental really study to understand the device performance, and because it doesn't have really the issues with, like, you have thousands of nanowires on the substrate, and sometimes it's hard to understand the sort of the fundamental device behavior. So that we normally use single nanowire as a platform to understand some the device properties. And then we can also make array devices. Normally what we do is that we actually spin polymers on top of the nanowire array to basically planarize them. And then we use some top-down etching to expose the top of nanowire so that we can make contact. And on back of substrate, we can also make another contact. So using this technique, we can also fabricate a series of different devices. So let me just give you a very quick overview of the single nanowire device that we have developed in our group in the past to 10 years time. So one of the devices we actually do is we use the single indium phosphide nanowire to make terahertz detector. So semiconductor, especially 3.5 semiconductors, being used actually as a photoconductive switch for terahertz detector application. So we want to see that when we actually using nanostructures such as nanowires, can we actually do also use them for terahertz detection, because they're tiny, so they can be really used for some really nice near field spectroscopy applications. And also because using nanowire, we can have very small sort of device volume, thereby we can really significantly reduce the dark current of the device, thereby can achieve good sort of signal to noise ratio. So that's really the motivation behind that. So what we do is that we knock down the nanowires on substrate, and through through the photolithography, we actually make this bow tie antenna across on each end of the nanowires. You can see from here. And then we measure the terahertz response through the terahertz spectroscopy system at Oxford University through our collaborator, Professor Michael Johnston's group, where we can actually see that from the nanowire, we are able to detect a quite broadband terahertz wave with broadband detection up to 2 terahertz with very good signal to noise ratio. So this is the signal measured from our single nanowire device. And we can see that this is has a very nice signal to noise ratio compared to a bulk reference fabricated from indium phosphide substrate, which actually Michael Johnston's group use quite routinely for their terahertz spectroscopy system. So this really, the reason is really because even we have a very tiny material, because we're able to reduce the dark current, use very small volume material that will reduce dark current, thereby we can actually get a good signal to noise ratio. And also again, by collaborating with Oxford and University, as well as University of Strathclyde, we actually demonstrate polarization resolvable detector by create this cross sort of nanowire network. As you can see that we create, 2 sort of nanowire channel through one on top of each other. However, they're not touched, so that we don't have this cross talk and sort of shorting problem. And then this has to be done using this transfer printing technique that developed in the University of Strathclyde. And as you can see from here is that when we detect the signal from this 2 channel of the nanowire at different polarization, when the terahertz incidence is polarized at different angles, we have obtained different signals from this channel. There's 2 nanowire channels. And then if we use this nanowire to detect actually a metal surface, which we know that they have different polarization response, we can see a very nice recover of the spectrum, very consistent with the simulation data, which is showing that nanowire is very, this nanowire terahertz polarization resolvable detector is very, very useful. Oh, just give me a second. I found this one. Almost run off battery. Forgot to turn on my switch. Okay. All right. So this is the terahertz work. And then, of course, this is a single indium phosphide nanowire without any other structures grow in this material. So we can, by introducing doping, we can actually also create PN junction into the nanowire, right? So this can be done just during epitaxial growth. We can grow PIN sort of axial junction nanowires. And so that's basically can serve as a nanowire solar cell. So by create that one, we can really, by developing this, electron beam induced current technique, we can really imaging in the SEM system that electron beam induced currents that's generated from the PN junction. So by doing that, you can see that if we've grown the PN structure in the nanowire, and this is SEM image, and when we do this EB current, you can see very nicely the current, EB current correlated to the built-in electric field inside the nanowire. So using this technique, we can really understand the device structure. So this is if we actually change the growth sequence by growing NIP to PIN. And you can see that the built-in electric field actually being profiles actually changed due to the different growth sequence, and then that's related to different growth rate during nanowire growth, as well as different doping distribution in this nanowire. So you can see this using this technique, using single nanowire, you'll be able to really give us a lot of give us a really insight of the nanowire growth as well as the device structure inside the nanowires. So doing that, we can also demonstrate good efficiency single nanowire solar cells. Of course, nanowire is a great material for laser because 3.5 materials already is great for laser and LED applications. So we want to look at their application in this space. So because of it, this is basically because nanowire have this nice sort of geometry. If you knock them down, the end facet is actually quite sharp. They can form quite nice sort of Fabry-Pro cavity in the single nanowire. So if you actually do the optical pumping, you can see the nano, you can see lasing from that. So that's really a nice sort of demonstration of the good material quality that coming from the architectural growth. And of course, if we can incorporate quantum well and also doping inside, we can actually make light emitting device. So this is an example where we're actually doing incorporate indium gallium arsenide growth into that, which I'm going to talk about very soon, into nanowire and fabricate into a single nanowire LED, which is having an emission wavelength at 1.3 micron. So this basically just showing that nanowire can be really used for a broad range of devices, solar cell, LEDs, and photodetectors. So as mentioned, single nanowire is great for the understanding of some, fundamental device and materials properties. However, it is, they are quite fragile and it's very hard for use and for a lot of applications. So what we're aiming is really develop nanowire array devices. So first, because we know that the nanowire geometry, because we have this one-dimensional geometry and they have nanoscale size. So basically, its diameter, spacing, height, and shape actually will strongly affect its dielectric properties, and we will affect in particular absorption and the light emission properties. Thereby, if we actually can design the nanowire array, the diameter, the pitch, we actually can tune their emission and absorption properties. So that's what we do in our group. We actually do numerical simulation to design nanowire arrays and use them to design, good absorption to achieve a broadband absorption in solar cells. We also can, we've shown that by tuning the diameter of nanowires, we actually can grow a nanowire array and through the same architectural growth that produce photodetector have a multi-wavelength response. We also have shown that by optimize the nanowire array and fabrication parameter, we actually can really enhance the nanowire LED light extraction efficiencies from 13% to over 70%. So apart from this optical design, of course, we have to develop good growth and fabrication processes to achieve these nanowires, to achieve a good device for performance. So that will be actually the focus of my rest of my talk. So firstly, I'm going to really talk about to develop quantum well inside the nanowires, because that's very important. The motivation of that is we want to develop light emitting devices. Of course, first we start with light emitting diodes rather than laser. Laser has a lot of important application. However, it's highly challenging to make nanowire laser due to both fundamental as well as some device fabrication related challenges. So we start with some LED structure, and of course LEDs also have a lot of important applications. If you look at the infrared LED, we're very familiar with the visible LED, the white, blue, green LEDs. However, infrared LED also have lots of important applications and also a very large market. And it's been normally used in, biometrics, the imaging, lighting, surveillance applications. And however, now more and more, there are a lot of more important emerging technology like Wi-Fi, holography, and optical communication now really looking at using LED as a light source rather than laser. So we believe there's a lot of important interest in actually developing infrared LEDs. And as just briefly mentioned before, we know that normally normal planar LEDs have very low light extraction efficiency due to this total internal reflection. So however, in nanowires, if we design our nanowire geometry properly, we actually can really achieve very high light extraction. And also, if we incorporate quantum wells in LEDs, in nanowires, basically it will be very important to have that, because the quantum well structure being widely used in laser diodes or LEDs due to their very high light emitting efficiency. And so our aim is really trying to develop this quantum wells in nanowires. So just a few words about the quantum wells introduction. When a quantum well is basically a heterostructure that formed by sandwiching a thin layer of small bandgap semiconductor between two layers of large bandgap semiconductor, such as gas-L gas or indium gallium arsenide, indium phosphide, which I'm going to talk about today. And quantum well has a very important advantage due to its quantum confinement effect. So having that quantum confinement effect really enhance the light recombination efficiency. And also if we change the materials thickness as well as composition, we can really do bandgap engineering. So quantum wells being really wide used for a lot of optoelectronic applications. And certainly we know that the Nobel Prize in Physics in 2000 actually been awarded by these two scientists for developing the semiconductor heterostructure used in high-speed optoelectronics. So that's really just highlight the importance of these structures. And of course, they share the Nobel Prize with the inventor of an electronic integrated circuits, Jack Kilby. So that's very interesting to see both, electronics and optoelectronics have important their importance is discovery. Okay, so basically when we grow the indium gallium arsenide, indium phosphide nanowires, as I mentioned before, for the the broad wide range of applications, we normally develop our sort of selective area growth at high temperature, about 700 degrees C and low 5/3 ratio, where we find that the structures are mainly based on a woodside indium phosphide, so which is a hexagonal sort of lattice. And then when we start to grow indium gallium arsenide quantum wells, we thought that would be quite simple. What we do is that during our growth, we can really switch off the indium phosphide source and basically switch off the phosphine and switch in the gallium and arsenic source. We'll be able to just grow indium gallium arsenide, because the quantum wells normally very thin, just few nanometers, we'll be able to do that. So we did that based on our general sort of indium phosphide nanowire growth recipe, and then just switch on indium gallium arsenide. And we can see that by just growing one thin layer, a few seconds of indium gallium arsenide, you can see that morphology of the nanowires changing from that beautiful hexagonal shape into this very non-uniform sort of structure and with a very strange shape on the top, right? So that's very interesting. So we don't know whether they're good or not. So we did PL and everything. Looks like we have got quantum wells. I'll show that later on. And then we actually tried to do the TEM, and we found that indeed, even though that looks very non-uniform, looks very strange, we have actually quantum wells form inside the nanowire. And then the quantum well have this sort of three different components. We have this actual component, we have this radial component, and the ring component, and a corner component, which actually showing different composition from the EDX mapping. So we basically have three different quantum wells inside. And if you do a more careful analysis of the structure, we found that it have a quite complicated complicated structure, like we have a mixed zinc blend and Wuzite segment across inside nanowire with different at different locations. So I won't go to the detail. You can see this paper. We have a very detailed analysis of the crystal structure. So how this morphology, so we're also trying to understand how the morphology is changed that leads to that. So what we find is that when we have the indium gallium arsenide grow on this Wuzite-based indium phosphide nanowire, what happens that it really depends on which facet the material is formed, and then you form different crystal structures. So on this radial sort of surrounding the indium phosphide, what happens that the radial indium gallium arsenide layer is quite happily adopt the Wuzite structure from the indium phosphide core. Now, however, on the top facet, what happens is that the indium gallium arsenide tends to really, because of the surface energy and also this the surface energy is lower, and then the indium gallium arsenide really wants to form a zinc blend structure on that. So then that, because of that, that's caused different growth rate at different facet, and then that create this inclined facet, and then that involves to all this different type of shape of the nanowires. So, but despite that very strange looking sort of morphology, if you look at the PL, we actually can get a quite nice photoluminescence from the nanowires. As I mentioned, we can, if you do the PL along the length of the nanowire, we can see there's a change of the PL peak, and basically showing that if we have the if we have the top of, if we put the laser on this position, we'll mainly get the PL from a strong PL signal from the actual quantum well. And when we move down to the bottom of the nanowire, only have the actual in peak reduce, and you have mainly very strong emission from the radial quantum well. So that's really, it's quite consistent with our TEM results. And then if we actually put in doping inside nanowires, as I just mentioned, we can actually create a radial junction PIN structure, and thereby we can really inject current to get electroluminescence from this nanowire. So you can see that this is the IV characteristics from this single nanowire, which is showing a good diode behavior, and you can see the electroluminescence increase with injection of the current. And then we want to say, okay, can we use it to making an array device? How is the light extraction will be affected by having this inclined facet nanowire? So we did a FDTD simulation really to compare, if we have this quite strange looking inclined facet nanowire as well with a more uniform sort of faceting nanowire. So with two types of shapes, so we have this shape is purely based on our nanowire growth. So you have a bottom hexagonal indium phosphide, Wuzite indium phosphide nanowire to start with, and then because of the evolution of the facet during the growth, and you can see a lot of triangular shaped nanowire electronic integrated. We compare that with sort of purely triangular shaped nanowire. And we find that actually the light extraction from the top of the triangular facet is only 13%, and then that from a very uniform nanowire with this triangular shape will have much larger sort of larger light extraction. This is mainly because of this inclined facet cause some disruption of the optical resonance mode, thereby and it leads to the optical loss. So this is certainly not very ideal. So we don't think this is a very nice structure to make. So that we'll have very nice light extraction from this inclined facet nanowires. So a student in Suk, he has come up with new ideas to really introduce this two temperature growth. So by reduce the growth temperature of the first step, so he wants to, by changing the growth temperature, he wants to really be able to change basically the energy during the nanowire growth, and thereby to actually change, to be able to really enhance the uniformity of the nanowire. So as you can see that there's something missing. This is one-step growth, and this is two-step growth. You can see that by using this two-step growth, he's able to really change the growth he's really able to really modify the shape of the nanowires and also improve the uniformity significantly, both in diameter as well as their length, and then to really introduce this very nice triangular shaped nanowire across the whole nanowire length. This is really by because of the surface energy change by modified growth temperature. So by this way, he's able to fabricate the array nanowire LED. As you can see here, the nanowire LED has quite nice emission, infrared emission, and then they have also quite nice electroluminescence coming from nanowire array LED. Of course, the power is still not very high, and that's something we are aiming at further improve. So, of course, also from the simulation, we can see that if you look at this inclined facet nanowires, I think there's a typo here. So this inclined facet nanowire, from the bottom of the nanowire, you can see that the light extraction is much higher than the triangular surface hexagonal bottom. So that means like hexagonal facets maybe have higher light extraction than that. And that's what we want to see. Can we grow hexagonal facet nanowires? So it turns out that if you look carefully in the literature, we found that people actually can grow indium phosphide nanowires with different facets, right? So I have mentioned that the facet with the indium phosphide nanowire we grow base is actually wuzite indium phosphide. It has based on a high growth temperature, low fiber-over ratio growth rate. And this Japanese group is actually shown quite nicely. If they change growth window to a lower growth temperature and a higher growth fiber-over ratio, they actually can change the nanowire facet to zinc blend. So you can see that although they all have hexagonal shape, but they actually have rotated facet. And because of this, they create this zinc blend 100 facet on the top. This actually, we think if we do that, we actually can facilitate indium gallium arsenide growth, which actually tends to form zinc blend segment on the top facet, right? So if we can create that, and then basically we probably will have that rotation of the facet during the growth. So that's basically our sort of motivation. We want to see if we can really create another growth window to create zinc blend based indium phosphide nanowires. So, so here's some further optimization. So my student Fan Lu, he spent a lot of time to optimize the growth rate. So we basically reduced the growth temperature, and we found that we can, and by increased he did a first investigation of 5/3 ratio by really increased 5/3 ratio from 80 to 3000. And then by also, again, further optimizing the growth temperature, he can really create this very nice hexagonal shaped nanowire, which really very uniform shape and no sort of distortion of the different shape. And if you look at also the TM, we found that we have this zinc blend and wuzite mixed phase. It's not pure zinc blend, but it's already good enough to really form very nice uniform nanowire array. And if you look at a PL, of course, we have different PL peaks from the segment, wuzite segment, zinc blend segment, as well as zinc blend wuzite sort of transition. But despite that, if you look at the carrier lifetime, we can still get quite nice about nanoseconds carrier lifetime, which is really showing that the nanowire has very good optical property. So based on this, we can in fact incorporate much more number of quantum wells. So we have done that up to 40 nanowires with very nice, beautiful sort of nanowire shape. And if you look at, so this is the cross-sectional TM showing that. And if you look at infrared cathode luminescence measurement, you can see that we have very nice emission along the length of the nanowires from this zinc blend-based indium phosphide quantum well growth. And if we use doing optical pumping, we also can see very nice, single lasing, single nanowire lasing from the quantum well at 1300. So that's just basic showing that the very nice optical property of the quantum wells. And of course, and we want to see if we can make array nanowires based on this zinc blend based quantum well nanowire. And so we can certainly do that. So you can see this light injection current injection at different levels. So you can see the increase of the emitting from the LED. And then this is the EL spectrum, basically have very broad LED spectrum, mainly coming from the radio and the different sort of quantum well components, as I mentioned before. And but we can see that the power output is much improved from what we've done before based on this triangular shaped nanowire. So we've got much improved. This is partly due to we believe it's partly due to the change of the nanowire shape from a triangular shape to the hexagonal shape. And of course, we also can modulate them quite fast. When we modulate through the electromodulation, we can do up to 1 gigahertz modulation of the LED, so which is really showing they could be really useful for optical communication. And also we show that if we actually change the design of the nanowire array, basically by change the pitch size, we can also tune the wavelengths of the nanowire LED, very broad wavelengths tunability. And this is mainly due to, when you have different pitch, you actually, the growth rates is different, and you actually have create probably different thickness of the quantum wells, or more, also maybe some composition will be varied, thereby you have this broad sort of wavelength change. So certainly we can further, reduce the array size. So here we just demonstrate like we can grow a very few nanowires on top on the substrate and then create. They're also working quite well, so which means that we probably be able to further reduce the nanowire array size to create a nano LED, to create a nano sort of light emitting sources, so that you can use that for multi-wavelengths, multi-pixel, and also individual addressable multi-pixel nanowire arrays for wavelengths multiplexing. So this is something we'll develop in the future. Of course, I have shown that we can also create multiple quantum wells inside a nanowire. So up to 40, we know that multiple quantum wells can be used to so that then if you have multiple quantum wells, you can able to create a lot of absorption, increased absorption layer. We can use that for photodetector applications. So we can show that when we incorporate in gallium arsenide quantum wells inside, we actually be able to achieve extended absorption, the photo detection from the indium phosphide around 900-ish to all the way to 1600 photo detection wavelengths due to the quantum well absorption. And then this quantum well photo detector also have very good responsivity, very good responsivity due to the basically the transport inside radio direction transport. And also we can modulate them at about 20 kHz at 3 dB frequency, which showing their relative relative fast as well. So we're showing that this indium gallium arsenide indium phosphide quantum wells can be also used for photodetector application. So I'll probably just use the last 5 minutes just to quickly talk about also nanowire array device actually can be fabricated by top-down etching. So we know that epitaxial growth is very expensive and also very, it's very, very expensive technique, and also it takes a lot of time to create, patterns and optimize the growth. So some of the nanowire device actually can be also fabricated using top-down technology, which also have very good performance. So just how we fabricated top-down, basically we just using a series of sort of masking technique, again, use silicon dioxide and nickel sort of as mask, and using ICP etching to basically do the top-down etching, create indium phosphide nanowire array. So here again, we are using just pure indium phosphide substrate to create different devices. So this device is indium phosphide, undoped indium phosphide substrate. We actually find that we can use them as resistive sensor to actually sensing nitrogen oxide, which is a very common air pollutant in the air, right? So to develop this kind of sensor is quite important. So what we found is that nanowire, because it's a one-dimensional large surface area geometry, provide a very good surface for the nitrogen dioxide absorption. And then because of the nanowire surface, also, but with the absorption of nitrogen oxide and also the surface defects, they actually facilitate electron transport from the nanowire into the nitrogen dioxide absorption on the surface. So this absorption actually, and also charge transfer, will lead into a conductivity change of nanowire. So this is how we, using this way, we can really detect. So detecting the current change, we're able to detect very sensitive nitrogen dioxide absorption. So of course, to fabricate this nanowire device, we're actually also using this tilde angle gold deposition. Thereby, we can expose half the nanowire surface to the nitrogen dioxide absorption to achieve this sensing. And it turns out that this sensing device, a nanowire-based sensing device, is highly sensitive. We're able to really detect a very high sort of limit of detection of down to 3 ppb level at room temperature. And it has a very high selectivity, as you can see that towards a range of gases, and with very good stability. So we also found that by changing geometry of the nanowires arrays, we can also tune the sort of response range of the sensor, which would be very useful as well. So that's basically really just showing that semiconductor, 3-5 semiconductor could be really useful for nanowire for actually sensing application. And we have recently also showing that by implementing a PN junction inside the indium phosphide nanowire array, we're able to do self-power sensing. So which will be, we're going to submit that work very soon. So another work we have done using indium phosphide top-down is actually making a radio heterojunction by forming, by depositing zinc oxide on top of that. So because zinc oxide and the indium phosphide have this very nice type 2 band alignment, we're able to, and also they were able to really create a very nice solar cell behavior, because the type 2, they block some carrier diffusion and then enhanced performance. And also we designed a nanowire array to have a very high absorption. Thereby we can actually achieve very high quantum efficiency in nanowire. So demonstrate 17% nanowire efficiency, which is one of the, I think the best reported value for the radio junction nanowire solar cells. Using a similar design, we actually again use it as a photo detector. So what we what we found is because of this very high surface radio heterojunction form on the nanowire surface, so and with very high field, we actually can really suppress the dark current significantly in this structure. Thereby, we can really detect a single photon level of the light. So you can see that when we're able to really detect the nanovolts type of the light very weak, and also operate them onto the self-powered mode. So I think I'm running out of time. So I just, so what we're going to in the future, so not only we want to create those very single component active devices, we would like to actually be able to incorporate that into highly integrated optical system. So recently funded by Australian Research Council, we have this a multi-million-dollar consortium called ARC Center of Excellence for Transformative Matter Optic System, where we're trying to really develop this highly integrated optical system by integrating light generation, detection, and with the very, the very versatile design of matter surface, to be able to, manipulate the light generation and detection, and to achieve the highly functional optical system that can be used for holographic display, night vision, variable sensing, LiDAR, remote sensing, and Wi-Fi technology. So where we all need this, highly integrated devices and also structures. So Just to conclude, basically, I hope I've give you a bit of, I hope I convince you that 3.5 semiconductor nanowires offer great potential for a range of device applications. We've also demonstrate that, in particular, the highly uniform 3.5 quantum well nanowires that will be very useful to for the future light emitting device, as well as photo light detection devices, we believe. And also, it is very important to understand, optimize this nanowire growth design and their structural, optical, electrical properties to achieve the high performance devices. So finally, I just want to promote this a new journal that's really on the optoelectronic space called Optoelectronic Advances, and it has excellent the board of the editors, and also its aiming at it's already have achieved the high impact factor of 9.6, and you're most welcome for people working in optoelectronics to submit your paper. So thank you very much for your attention.
Thank you very much for the wonderful presentation. I know we did start a little bit late. We do have some questions, hands being raised. I know it's later for you, so are you available to stay with us for another few minutes to address those questions, Professor?
Oh, absolutely, yes. Yeah.
Great. In that case, I'd like to call up Busairi. You had a question in the chat. Are you still available to ask that question to Professor Fu? If so, you can unmute yourself, and I will be, or you have another one coming straight through. So if you want to ask that question directly, you can take the floor and pose that question.
Well, I can see the question. I can repeat it. I guess this talking about the growth temperature I'm using for growth of the quantum wells on the top of the wafer, or just from the susceptor. I think in our configuration, this one is on top of the wafer because we're using the top sort of shower head. I believe our sensor is from the top. So that's the I probably can't give you a conclusive answer for that because we have two MOCVD reactor. So I think one of the reactor we actually measure from susceptor, the other one's from the top. I can't exactly show that structure what it is, but what I can say is that most of, I think, we just sort of monitor the temperature for that particular things. I think we're just really using both technique to monitor the temperature, and we'll have to do some adjustments. So that's a range rather than a very accurate temperature there, I have to say. Yeah.
Great. And there was actually another question as well about typical sizes of your nanowires, the cross section and length. Can you comment on that as well?
The shape, how to control the growth of nanorods as accurate to grow in the shape of what is AMU?
I think it's the wait on the slide where you showed the AMU logo. I think that's
ANU logo. How to actually control? ANU logo. Sorry, yeah. Oh, so that's so the shape you can't, but okay. So the array you can design it. So what we do in that ANU logo is that we just design a pattern. By just writing using electron beam lithography, we design the pattern. So you can see the nanowire is spacing. Yeah, it's just as when we design the spacing, this example, right? You can pattern that. So what we do is like we just, pattern a few nanowires, group them like that as the design. That's how we do that. So that's from electron beam lithography, yeah. And then you can actually see that the nanowire shape is not perfect. You always have some big nanowires on the border and inside them more regular. So that's one of the issues we actually have to address. It's not totally uniform on the when we go very small scale.
Great, thank you for that answer. And we have Gali Solito, who's just come online with the camera. You had a question in the hand raise. So Gali, the floor is yours.
Thank you very much. Dr. Fu, it was really a really exciting presentation. In McGill, we try to go beyond nanometer scale VLS. So in my group, we try to do a micro scale VLS for lateral epitaxy of indium phosphide on silicon. And at this step, we try to do selective etching of indium phosphide. And I saw that in your top-bottom approach, you use the ICP process. But I think would appreciate if you could have give more details, because you kind of like quickly skim because of time, I guess.
You mean the ICP?
ICP of indium phosphide.
Indium phosphide one. Yeah, I don't know whether I have the details here. Yeah, we're just using chlorine based, but if you want the details, I can provide you later on. We do need to do a lot of a detailed sort of optimization of that. So okay. I believe in this paper, I have, but if you shoot me an email, I can give you more detail of like flow rate and all this. I just don't have that in my presentation at the moment.
Sounds good. I will take a look in the paper and contact you if necessary.
Yeah,
and
sure.
Maybe one more question, if that is okay. Are you also aiming for a single photon emitter for these nanowires?
We don't, myself don't, because, but we do have in our group other colleagues actually trying to do some single photon emitter work and trying to grow quantum dots into the structures. And also, we also actually grow boron nitride using our nitride reactor. Those material can be used as a single photon emitter. So we've got a publication in that, but it's not my work.
Thank you very much.
Yeah.
That's great. And
try to grow nanowires on DBR for weak cells. No, we're not working on that yet, because it's quite challenging to grow those, actual sort of heterostructure. So we haven't done that. But are you saying like we can grow a planar DBR and then nanowires? So that's probably possible, but we are not doing that at the moment.
Wonderful. Thank you for taking that. If I may take my moderator privilege and ask you a question, it's really exciting to see how you're going into sort of design aspects moving forward. Do you see a route with these 3.5 nanowire arrays to almost go into a level where to integrate this process design kits that will help really designers transfer their ideas to the fabrication and better validate their testing as well in the future?
Well, the 3.5 is being really used everywhere, right? But a nanowire to me is still really a sort of in the development side. I think that's why it's important we're doing all this foundation work and trying to really see what kind of area they can be really used for. I certainly believe there will be a further development. We're actually working on that, basically. But I think a lot of array-based device, and I think a lot of things is really trying at the moment is trying to understand what's the limitation and what are the potentials, right? And once we're doing that, I do believe there will be a way, because everything is moving toward that direction. The matter surface is something like a similar sort of structure. Nanowires, this kind of structure, and if we want to really develop this very highly integrated systems, you want this miniaturization and integration. So I do believe there will be, but it's not at the moment yet, still in developing. One thing also I haven't touched on, we're actually also making flexible sort of device. We can really peel the nanowires away from the substrate. We can actually making them flexible device. So that's also give you another way to integrate and also into different applications, I think.
Yeah, I have to say, today was a great insight into all the applications that can be achieved with nanowires. And looking at that fabrication and all the modeling and testing your group has done. So I do want to take the opportunity to thank you again, give you a round of applause virtually, of course, from everyone that's in the room. I don't see any more questions today, so I see some claps coming through and some people who are really grateful, and thank you for your time and response to these questions. So thank you very much, Professor Fu, for
thank you very
being
much
with us,
for
and
thank you for inviting me.
and staying up past the day for you. It is today the 10th of June for you now, so we really appreciate you accommodating for the Eastern time zones and everyone in between. So from me and everyone, thank you very much.
Thank you. All right. Bye, everyone.
Bye-bye.
Yeah, thanks, Professor.
Bye, thanks.
Okay, bye, Matthew.
Goodbye, Ajay. Thank you.